Hi, in this video we're going to compare binary search trees to hash tables. We're going to see what the trade-off between the two of them are because they're kind of directly comparable. So we've seen two different competitive implementations of the map abstract data type. Remember, the map abstract data type has the following major operations. You can create an empty one, you can search for a key and get a Boolean if they exist that's contains. You can find a key, find the pair holding a key. You can insert a pair, or you can erase a key. And we saw that we can use an AVL tree. And if we use an AVL tree, then the create operation is constant time, and all the other operations are logarithmic worst case time. And we've also seen that we can use a chained hash table, and the chained hash table also takes constant time to create, and all the other operations are constant expected time and linear worst case time. So here's that information summarized as a chart. And they're tied on creation. That's you usually only do that once, but in basically all of the other categories, the trade-off here is the AVL tree takes log n time and the chained hash table takes constant expected time or linear worst case time. So how do those kind of shake out? So again, every AVL operation is logarithmic worst case time, and these chained hash table operations, they're randomized, so there's a random aspect to this. It's constant expected time, but linear worst case time. So what exactly is the trade-off? Well, constant is faster than log n, and log n is faster than linear. So hash tables are usually faster than binary search trees. You know, constant is faster than log n, so most of the time a hash table is quite a bit faster than an AVL tree. The hash table handily outperforms the binary tree usually. However, a hash table operation could take linear time, and linear time is slower than log n. So there's a slim chance that if we're really unlucky with the hash function that we choose, that our hash table could be as slow as big O of n, and that's much worse than log n. So the hash table is maybe a little bit of a gamble. Usually it's a lot faster than a binary search tree, but there's always this slim chance that the hash table will be slower. So that's kind of a remote but realistic possibility. There's a slim chance of that. It's not a very likely thing, and as the table gets bigger, it gets less and less likely, but it is a non-zero possibility. It can actually happen. So again, binary search tree operations are always log n time. It's not the fastest efficiency class, but it's still fast. It's a fast operation, and this is kind of provably dependable. So you know if you use a AVL tree or some other self-balancing binary search tree, every one of those search, insert, and erase operations is going to take logarithmic time, which is fast. Also, binary search trees have that binary search tree order invariant, which means that the keys are always in sorted order. Hash tables don't do that. By design, hash tables scramble up the location of every element, so they're not in any sorted order. Occasionally, that sorted order is useful. Hash table operations, they're usually constant time, and constant time is even faster than logarithmic. So hash tables are blazingly fast. They're really fast usually, but rarely they could be slower. They could be log n time, kind of tied with binary search trees, or they could even be linear time, which is substantially slower than binary search trees. So constant is the fastest possible efficiency class. There's no efficiency class faster than constant, so that's as good as it gets. And hash tables are a pretty good general purpose choice. So kind of by default, if we want a map, usually we reach for the hash table because it's faster usually. However, this small but non-zero chance of being quite a bit slower is a liability in situations where we can't have any one operation be slow. So this is namely real-time systems. We've talked about this before. This was kind of a thing with vectors versus linked lists. A real-time system is some kind of system that needs to make quick responses with a predictable response time. So that would be video games that need to render 30 frames per second or 60 frames per second. We don't want these rare hiccups that are slow. Or self-driving cars need to be monitoring the driving situation. You don't want a slow operation to disrupt that. Other kinds of physical controls of robots or factories or things, embedded systems, these are other computers that control physical devices. In those kind of applications, we might not be tolerant of this slim chance of a slowdown. So here's the decision tree I would recommend for deciding between a binary search tree and a hash table. The main difference is that hash tables are faster usually, but have two deficiencies. One is that binary search trees keep the keys in order, and also binary search trees have this provable, consistent performance with no exceptions. So here's the decision you have to make. If you need the sorted order of the keys, or if you need the operations to be non-randomized, so they always take the same amount of time and you can tolerate the operations being a little slower, logarithmic time versus constant, then use a binary search tree. But in any other situation, use a hash table. So if you don't care about sorted order and you're okay with a little bit of randomness in the runtime in the name of making it faster on average, then use a hash table. And because of that, that's kind of the general purpose choice. Usually I would say use a hash table unless you have one of these specific reasons to use a binary search tree. I'll mention that this is similar to the trade-off we saw between linked lists and vectors. There was a similar situation where vectors are faster in terms of constant factors, but they have that occasional resize, whereas linked lists are slower by constant factors because they're non-contiguous and do more memory allocation and freeing, but have very predictable runtime. And so it was a similar decision. If you needed a totally predictable runtime and you could tolerate things being a little slower by constant factors, use a linked list. But in any other situation, the vector is the better default choice. And that's why we see in C++ and a lot of other programming languages, kind of the default container is a vector. Similarly, the default map is usually a hash table.